Hello, and welcome to this GI 2020 talk. My name is Prashant, and I will be presenting the paper Fine Feature Reconstruction in Point Clouds by Adversarial Domain Translation. A point cloud is a set of points sampled from a surface in 3D. If the sampling density is not high enough, we risk losing some geometric features, which we refer to as fine features. And if these fine features are lost due to undersampling, it is impossible for any 3D reconstruction algorithm to recover them in the general case. However, deep learning techniques enable us to train a learned prior on a particular domain of data, which allows a 3D surface reconstruction algorithm to hallucinate what the surface might look like for a particular class of 3D surfaces. Just for context, there have already been several recent applications of deep learning to point cloud consolidation, most of which build upon the PointNet++ network architecture. Out of these methods, the method called 3PU was found to yield more accurate reconstructed surfaces than any of the previous methods. In this work, we propose harnessing the power of a deep learning model known as a conditional GAN to improve 3D reconstruction of fine geometric features. This is a novel application of conditional GANs because we normally associate them with 2D photographs, so it demonstrates their versatility in a 3D geometry problem. Now let's talk about generative adversarial networks, or GANs. A GAN is an unsupervised deep learning model with two subnetworks, a generator and a discriminator. The discriminator learns to distinguish between realistic and synthetically generated data, while the generator gradually learns to generate realistic data that fools the discriminator. GANs have proven to be very effective at generating realistic, novel 2D images that appear to be sampled from a particular domain, such as portrait photos of celebrities. Now we know that GANs can generate realistic images in an unsupervised setting, but to make them truly useful, we need to be able to apply them to supervised learning problems. That's where conditional GANs come in. The generator outputs of conditional GANs are conditioned on their inputs, which allows us to generate realistic images from a particular output domain, which are structurally similar to an input image from a different input domain. In other words, we are translating images between two different domains, such as street maps and satellite images, or sketches and photographs. Now, coming back to our 3D reconstruction problem, we are trying to reconstruct detailed 3D surfaces from point clouds. We can bridge the gap between these two domains, point clouds and 3D surfaces, by representing local neighborhoods as height maps. Point cloud neighborhoods are represented as sparse height maps, while 3D surface neighborhoods are represented as dense height maps. We can now train a conditional GAN to perform domain translation between sparse and dense height maps. Our training data is a set of 90 3D meshes of statues obtained from Sketchfab. This is the same training set used for the state-of-the-art point cloud upsampling method called 3PU. Each training example is a corresponding pair of a sparse and a dense height map for the same local neighborhood. After training the conditional GAN using the popular pix-to-pix method, we can generate a plausible dense height map for any sparse height map that we obtain from an input point cloud. The dense height map generated by the GAN is then sampled according to one of three predetermined sampling patterns to generate a dense set of points. We can also compute normals at the newly generated points by applying backward differences on the dense height map. This allows us to apply screened Poisson surface reconstruction on this dense set of points to reconstruct the surface. Here are some of our results on Sketchfab models of statues that were not used in training. We can see that a considerable number of fine details are recovered after applying our method. Next, we evaluate the performance of our method using three metrics applied on the reconstructed surface: distance to the ground truth mesh, Hausdorff distance, and chamfer distance. Our experiments showed that out of the three sampling patterns, the one that we refer to as the detailed pattern generally had the lowest error, although the even pattern gave better performance for very sparse point clouds. We also made an interesting observation through another set of experiments. Even after training the GAN on sparse height maps from dense point clouds with hundreds of thousands of points, the model is able to generalize quite well when tested on sparse height maps from sparse point clouds with 5,000 or even as few as 625 points. Performance-wise, we observed that our method takes about 20 seconds to process 5,000 points and 3 minutes to process 160,000 points. That's with a mid to high-end consumer GPU. We have also performed a large-scale quantitative evaluation on the first 1,000 3D models from the ABC dataset. These are mostly CAD models, but we use the same GAN that we've already trained on the Sketchfab training set. For comparison, we use the state-of-the-art point cloud upsampling technique called 3PU. 3PU processes patches of points from a point cloud by passing them through several upsampling units that are loosely inspired by PointNet++. Its final output is a dense and evenly spaced set of points, having 16 times the original number of points. So after estimating normals, we can use the same evaluation procedure for both 3PU and our method. What we found from the experiment is that our method is quite competitive with 3PU in terms of the accuracy of the reconstructed surfaces, despite how different the two methods are. Remember, our method generates height maps using a conditional GAN, while 3PU processes patches of raw points directly. We should also note that the error values on average are smaller than the length of an edge in a ground truth mesh. These ground truth meshes are densely sampled and normalized such that most edges have length 1. This shows that we are indeed reconstructing fine features from the input point clouds. Another cute application of this domain translation method is that we can easily adapt it to upsampling point clouds while simultaneously interpolating a pre-computed scalar field. This is especially valuable if the scalar field is easy to compute on a mesh but expensive to compute on a point cloud. That is certainly the case for the sharpness field, which is something I presented at GI 2 years ago. Here we can see that recomputing the sharpness field from scratch on an upsampled point cloud is far more expensive than using the GAN to predict what the values ought to be, given the pre-computed values for the low-resolution point cloud. But why stop there? We could also think about upsampling other kinds of scalar or vector fields. So that might be an interesting direction for future work. Thank you for listening to this presentation. We invite you to read the paper for more details on our method and the experiments. You can find the link to the paper in the description box below the video.